So now we are going to continue Unit 2 by doing a review of linear equations. And even though you've done this for several years, this is so important because we'll use it so often, and it's the basis for what we will build upon. So as anytime you're working with linear equations, one of the main things you'll need to know is slope. Remember, slope is represented just with an m, and we call it rise over run, change in y over change in x. This right here is a Greek symbol, it's delta, and that is what means change in. So that's good to know, that's another way to represent it. But the equation you normally use is m equals y2 minus y1 over x2 minus x1, and of course you'll have to know that. Sometimes we do get confused and want to put the x's on top, so if it's helpful to remember rise over run instead, do that as long as you know how to find slope using 2 points. Remember, slope is often called the rate of change. So we have our three equations that you can use for writing equations of lines, linear equations. Point slope, normally we use point slope when we have a point and we have a slope. M is still our slope from before, and then our point is x1, y1. Our x and y are our variables, so they're going to stay x and y. What's important to note about point slope is that if you want something in slope-intercept form, you can start in point slope and then solve for y, and then it will become in slope-intercept form, and so a lot of times that's easier if you do that instead of trying to start out in slope-intercept form. But slope-intercept form, of course, is y equals mx plus b, where m is still slope, b is your y-intercept. And then you have your standard form, which you probably haven't used as much in the past, but we will be using some. This can also be called the general form. It's ax plus by equals c. But a couple important things to note. So your x and y have to be on the left, and your constant on the right. Your a, b, and c, so all your numbers, all your coefficients, all your constants have to be integers. So if they're fractions, you'll need to multiply by the denominator to cancel out that denominator and make them integers. A should be positive and it should come first. So if you have like a negative 5x, you'll need to multiply through by a negative so that A is positive. So x and y on the left, x comes first, x is positive, and then all of them are integers. So calculate the slope of the line through the point. I want you to pause, use your slope formula to do 1, 2, and then check back. So you remember you can label x1, y1, x2, y2. It doesn't matter which ones are your 1s and which ones are your 2s, as long as your x is first and your 1s go together and your 2s go together. So I calculated slope for number 1 and got -3, and if you would have calculated a different way, you still would have gotten the same thing. On number 2, I got 4 over 0, and sometimes we struggle to remember if that is undefined or if that's 0. So the way I've seen to remember it is if you have a 0 on bottom, no, that's not okay. That makes it undefined. But if you have a 0 on top, that's okay. That just makes it 0. So I do have a 0 on bottom, so this slope is undefined. We don't want to say no slope. It doesn't have a slope, that's correct, but I don't want you to confuse that with 0. It has an undefined slope. And in just a second, we'll talk about what specifically that line is. So we just worked the slope for number 1. Now write an equation for that in both forms. You have slope and you have 2 points. You can pick one. Of course, it doesn't matter which is which. Write that in point slope, and then you can solve for y and you'll get it in slope intercept. So using the slope that we had from number 1 and one of the points, again, it didn't matter which one, I wrote the first in point slope because I had my point and I had my slope. And then notice this is the m. These happen, your x1 and your m happen to be the same. But I distributed and solved for y, and this is my slope intercept. So there's both my equations, just in a couple of steps. So just to review, we're going to write the equation in slope intercept form. So this is, always pay attention to your units. So -1, -2, -3. So that's my b. And then we can look at our slope. So we rose 1 and ran 2, but it was 2 to the left. So that rise, I went up 1, and my run, I went left 2. So that is going to be a negative slope, -1/2, and then we can throw it into our slope intercept. Or you could have picked a point and a slope instead of using the slope intercept, but if you do have the intercept, slope intercept's the easiest way to go. So as a review, you've probably seen your slope tree. If a line is going this way and that has a positive slope. So again, I know this is a little bit elementary for you, but just to review, because if we can catch ourselves from making little mistakes, then we'll help us out a lot. So there, your negative ones are going this way because it's often easy for us to look at a line and calculate the slope, but we'll forget to check whether we went left or down and made that negative. So there's that. And then you have this, which this is a horizontal line, like the horizon. And the way I remember it is a horizontal line has an O in it, so has a slope of 0. And then we have our vertical line, and that is no slope, which is the end slope. So that's what we'll use. So just as a reminder which ways those go. Now I want you to work number 5. So take this equation, solve for y to get it in slope-intercept form and graph it. And then once you've done that, work number 6, follow the rules to get it in standard form. X first, y second, both of those on the left, everything integers, x positive. And then check back to check your 5 and 6. So number 5, I solved for y, and there's my slope-intercept equation. I started down here, the intercept counted up 4 and over 7. Don't forget, I would expect you to use a straight line, to use a straight edge to draw your straight line, and of course we'll have to have arrows on the end. You could have done this in a different order. I started by multiplying everything by the denominator to cancel it out, move my x and y to the left, but my x had to be positive, so I changed all the signs, and there's my standard form. On number 7, we're going to use the equation from 5, but we're going to find our x and y intercepts. You might want to make note of this if you don't remember. How you can find your x-intercept is plug in 0 for y. How you find your y-intercept is plug in 0 for x. When I ask you for an x-intercept or a y-intercept, I want you to write that as an ordered pair. Okay, so work this and graph it and then check back. Okay, so I took the equation from number 5, and then for x-intercept, plug in y equals 0, and I got 3.5 or 3 and 1/2 is 0, and I graphed that over here. And then y-intercept, I did the opposite and got 0, -2. And if we used our straight edge to connect these, hopefully a little bit better than that, you can see that it's the same graph as number 5, just instead of having this point, we had a point out here. And so that was just another way that you could graph that. I will expect you to know how to find x and y intercepts using any equation. Okay, so number 8, the number of times a cricket chirps per minute depends on the temperature. The number of chirps in 2 seconds for 2 different temperatures are shown below. First thing we need to do is draw a graph, and then we're going to write an equation in standard form that models the situation. And then we're going to answer the third question, where if the temperature is 70 degrees Fahrenheit, remember our units are important, how many times would a cricket be expected to chirp in 1 minute? So the first thing we need to do is kind of figure out what data we have here. So we have temperature and we have chirps. And it tells us the number of times it chirps depends on the temperature. So that means the temperature is our independent variable. Temperature is going to be x. And then the number of times it chirps is y, because that is dependent on the independent variable on the temperature. So just to write that out so that we have it, we need to define our variable. X is our temperature, it's going to be in Fahrenheit. Y is the number of chirps. Okay. And specifically, we'll get into some time frame there. So if we write out our ordered pairs, what we have from this data here is at 40 degrees Fahrenheit, we get 0 chirps, and at 93 degrees Fahrenheit, we get 8 chirps. Now, these are per 2 seconds, so it's not actually per minute, like this says up here, but that's not how we defined it. That's okay. We can define it as per 2 seconds, because that's the data we have. As long as it's all the same, that is totally fine. So we need to draw a graph. Of course, we're only working with our first quadrant, and we need to label our temperatures Fahrenheit and our chirps. And again, we're doing per 2 seconds. Okay. And then we have 2 points, but that's all we need for a line. So I'm going to count by 20s down here. And then we have to go all the way up to 8 here. So we have 40 and 0 was our first point. Well, sorry. And then we can graph our other point of 93 right about here and 8. And 2 points is all we need for a line. So that's kind of the trajectory we're going on. Now, in reality, we know that we would not be using this part down here because we can't get less than 0 chirps. Okay, so that's number 1. We drew a graph, we labeled our axis, all of that, so that's wonderful. Number 2 says to write an equation in standard form, but it really doesn't matter what form we're writing it in. We need to start with writing our slope, finding our slope. So we can do this like we just did off of our graph. We have points here. We have the points we graphed. And we can write it like this. Now what I am going to do, since this is standard form, here we put it was for 2 seconds, but we are working in standard form, and our problem here does say per minute, so let's go ahead and convert these, and we'll start working per minute. We could have done that earlier. It doesn't really matter. And as long as you told me what you were working in, you don't have to do it at all. Like if you still want to keep working in number of chirps per 2 seconds, that's fine. But just to kind of practice a tiny little conversion, let's go ahead and while we write the equation in standard form, let's use excess temperature in Fahrenheit. Then we're going to do number of chirps per minute. That way we can just kind of see it 2 different ways. Okay, and so I still have 40, 0, and I have 93. The only thing that changed was it was 8 chirps per 2 seconds. I need that to be per minute. So there's 60 seconds in a minute. And so that's our new point. I want you to pause here and calculate slope and write your equation in standard form and go on to work part 3 of this question. Okay, so after we took our 2 seconds and multiplied by 30, since there's 60 seconds in a minute to get this, I calculated slope and plugged in. I plugged in a point slope, but one of our points did have 0, so that helped us out. And here is our equation. We do need to write that in standard form. So we're going to have to multiply. You can multiply by a lot of things, but since it's a 0.5, the easiest things can be 2. And then get everything to the left. So do that if you haven't done that. So once I got to that point, I was able to do what we did earlier to get it in standard form. And of course, you might have taken a different order. Then I came up here and I plugged in, and you could plug into either equation, but it said when it's 70 degrees, which is my x, what are the chirps expected to be in 1 minute? Now, if we hadn't converted a second ago to minutes, we would have to convert now. So that was a good thing we did that. We got our answer, and it's 135 chirps per minute.